This question tests my understanding of how the WEIGHTS parameter in scikit learns KNNImputer, K nearest neighbors imputer, works. I need to figure out how different weight settings change the way missing values are filled in. Think of it as a detective game, where I must find the best strategy to fill in the missing pieces. This sets the scene. I'm using a tool called KNNImputer from the Sklearn library to deal with some missing numbers in my data. My data has 5 different characteristics, features, and some values are missing, shown as NaN, which stands for, not a number. I'm going to experiment with different settings of this tool to find what works best. This statement says that if I use, then every nearby data point counts the same when I calculate the average to fill the gap. It's like a democracy, each neighbor gets one vote. This statement explains that when I set, closer neighbors get more say in filling in the missing value. The farther away a neighbor is, the less it affects the average. It's like an election where those living closer to the candidate have a bigger voice. This statement explains a special case. If I only consider one neighbor, it doesn't matter if I use uniform or distance weighting. The result is the same because there's only one neighbor to consider. This title introduces the core topic, understanding how the weights parameter functions within scikit-learn's KNNImputer, a tool I use for filling in missing numerical data in my datasets. I'll be focusing on the different ways I can assign weights to neighboring data points when calculating imputed values. This is the quiz question. I'm asked to identify which statements accurately describe how the weights parameter in KNNImputer works. It's a multiple-choice question testing my understanding of NImputer's functionality. This statement claims that setting weights to uniform means each neighbor contributes equally to the average value used to fill in a missing data point. I need to determine if this is true or false based on my knowledge of KNNImputer. Statement B says that using weights equals distance means that closer neighbors have a stronger influence on the average used to impute missing values than further neighbors. I'll check if this aligns with how distance weighting works in KNNImputer. This statement examines a specific scenario. What happens when I only consider one neighbor, n_neighbors equals 1? I need to consider if the choice of weighting, uniform, or distance, even matters in such a case. Statement C states that the weights parameter only applies to categorical data. I'll verify if this is correct, considering that KNNImputer primarily works with numerical data. I see this as a multiple-choice question testing my knowledge of the weights parameter in scikit-learn's KNNImputer . It's focusing on how different weighting schemes affect the imputation of missing values in numerical datasets. Let's dive in. This statement describes the uniform weighting option. I'll use this when I want each of the *k nearest neighbors to contribute equally to the average that fills in a missing value. It's simple and straightforward. Think of it like a democracy. Each neighbor gets one vote. Here, the distance weighting is explained. This time, I'm giving more weight to closer neighbors when computing the average that fills in missing values. The closer a neighbor, the stronger its voice in determining the imputed value. This statement explores the special case where I only consider one neighbor, n_neighbors equals 1 . In this situation, whether I use uniform or distance weighting makes no difference because there's only one neighbor to consider. It's like having only one vote. It doesn't matter if the vote has a weight. I'm focusing on the KNNImputer algorithm's weights parameter. This parameter controls how KNNImputer considers its neighboring data points when filling in missing values. Think of it as deciding how much influence each neighbor has on the final imputed value. This is the core question. We'll evaluate each statement to determine whether it correctly describes how the weights parameter works within the KNNImputer algorithm. Let's consider statement A. If you set, I'm using each neighbor equally when computing the average to fill in the missing spot. It's like a simple average. Now, statement B deals with. Here, closer neighbors matter more. Their influence is inversely related to their distance from the missing value. The closer a neighbor, the greater its impact on the average. Statement D addresses a special case. If I only use one neighbor, then the weight doesn't matter. The imputed value will always be exactly the value of that single neighbor, regardless of whether I choose or. Statement C is incorrect. The weights parameter only works with numerical data, not categorical data. KNNImputer handles numerical data. This question tests your understanding of how the WEIGHTS parameter in scikit-learn's KNNImputer works. We'll explore different scenarios to see how it affects imputation. If you choose, the closer a neighbor is to the point with missing data, the more it influences the imputed value. Think of it like a weighted average where closer neighbors have a louder voice. If you only have one neighbor, it doesn't matter whether you use or. The imputed value will always be the same as that single neighbor's value. It's like having only one vote. The weighting scheme is irrelevant. When I select, every neighbor gets an equal say in determining the imputed value. It's like a simple average where each neighbor's value contributes equally. This statement is incorrect. The WEIGHTS parameter only works for numerical data. KNNImputer isn't designed for categorical features. This title tells you that we're diving into the weights parameter within scikit-learn's KNNImputer . I'll explain what this parameter does and how it impacts how missing values are filled in. Get ready to learn. I'll explain what this means. Imagine you're filling in a missing grade. With weights equals distance, if your neighbor's grades are close to yours, their influence on filling in your missing grade is higher than a neighbor with distant grades. The closer the neighbor, the stronger their influence. This statement is false. The weights parameter only works for numerical features. KNNImputer doesn't directly handle categorical, like colors or categories, features, so this parameter is irrelevant for them. Let's break this down. n_neighbors sets how many neighbors are considered. If only one neighbor is used, it doesn't matter if you give it equal weight, uniform, or a weight based on distance, distance. The imputed value is simply that neighbor's value. It's like having only one opinion to consider, it's the only option. Think of it like a democracy. Each neighbor gets one vote. Every neighbor's value contributes equally to the average used to fill in the missing value. No one neighbor's opinion outweighs another's. This sets the stage for the quiz. You need to determine which statements about the weights parameter in KNNImputer are correct. This is the title, highlighting the focus on the weights parameter within the KNNImputer, a machine learning tool used to fill in missing values in datasets. It's like the main topic of our discussion today. Let's dive in. This poses the core question regarding the weights parameter within the scikit-learn library's KNNImputer function. We'll analyze each statement to determine whether it's true or false. This is the quiz question we need to answer. This statement says that choosing uniform in KNNImputer means each neighbor contributes equally to the average for missing values. I find this true. Think of it like a democracy. Everyone gets one vote. Simple and fair. This statement says that selecting distance weighting gives more importance to closer neighbors. I see this as true, too. Imagine a group project. The closer teammates contribute more to the final grade. Makes sense, right? This one claims the weights parameter only impacts categorical data. I disagree. The KNNImputer is designed for numerical data, so this statement is false. We're only dealing with numbers here. This statement says if we only consider the nearest neighbor, n_neighbors equals 1 then, uniform, or, distance, weights give the same result. I think this is true because there's only one neighbor, so its weight doesn't matter. It's like having only one vote in an election. The result is the same whether that vote is equally weighted or more weighted. This specifies the type of data we are working with. Numerical data with 5 different characteristics. It reminds us that this technique only works for numerical values, not for categories like colors or types. This is crucial context for understanding the problem.